Hello, I'm Takashima from Kyushu Institute of Technology, Japan. Today, I would like to talk about our recent work on surface shape changeable tactile sensor using shape memory polymer. In recent years, robots have been used not only in environments with limited space such as factories, but also in a wide range of fields such as nursing and welfare. The tactile sensors that are used in these kind of robots have an elastic cover based on to the surface of the pressure sensing element. This elastic material requires high flexibility, elasticity, and deformability. When a force is applied on the surface, the perpendicular stress distribution at the top of the pressure sensing element under applied pressure becomes broader when the elastic material is more rigid. The following describes the advantage of the rigid and flexible materials. Rigid materials prevent scratches on the sensor surface, detect force using a small number of pressure sensing elements since the stress distribution is broad. Flexible material absorbs the shock of impact. Improves the spatial resolution by increasing the number of pressure sensing elements since the stress distribution is narrow. Given these advantages and disadvantages, although it would be ideal to use elastic materials with different rigidities depending on the robot usage situation, it is difficult to replace the material once it has been passed on. Therefore, in the present study, we exploit the inherent advantage of shape memory polymers, SMPs, for use in tactile sensors. Shape memory polymers, SMPs, can be deformed above their glass transition temperature Tg by applying a small load. This is an SMP sheet. This is a hot water. Below Tg, the SMP is rigid, like this. SMPs can be deformed above Tg by applying a small load, like this. They maintain their shape after they have been cooled below Tg, like this. They return to the predefined shape when heated above Tg. This is the relationship between the elastic modulus and the temperatures. As shown in this figure, the reversible change in the elastic modulus between the glassy and rubbery states of SMPs can be of the order of 100 to 1000 times. Since the elasticity of an SMP changed depending on the temperature, by applying a SMP as an elastic cover for tactile sensor surface, this type of tactile sensor with an SMP has the following advantages. For example, the spatial resolution and the rigidity can be changed, and it is necessary to replace the tactile sensor to match the application. Even for industrial robots, there is a need to operate under a wide variety of specifications and environments to handle high mix, low volume production, and this case can also be handled. Unlike humans, there are many animals that change their shape when they sense danger, such as armadillos and woodlice. Using an SMP, it is possible to construct a robot that protects itself in the same way, by changing its surface rigidity when external dangers are sensed. Moreover, the surface shape can be changed according to the situation. It has been reported that frictional and tactile sensor output can be changed by varying the surface shape. For example, a fingerprint structure is effective for measuring microtexture. In a previous study, a prototype sensor was fabricated using a SMP sheet with embedded electrical heating wires. This is a photograph of the prototype sensor. Using this prototype, its fundamental performance regarding advantage 1 was evaluated. However, disadvantage 3 was not evaluated in our previous study. Therefore, this research uses the shape fixity of an SMP to evaluate the output from a tactile sensor when traced along a bumpy surface. This figure shows a schematic of the operation when a tactile sensor using a shape-changing SMP is mounted on a robot arm. When it is desired to fix the shape, the SMP is heated to make it flexible, and it is then pressed against an object that has the desired surface shape, as shown in this figure. When it is cooled, this shape remains like this. A photograph of the prototype sensor used in this study is shown in this figure. This tactile sensor consists of an SMP sheet on a silicon rubber sheet pressed on a rubber sheet including pressure sensing elements, fabricated in our previous research. In this study, we used polyurethane SMPs. The fundamental characteristics of the SMP are listed in this table. This figure shows the external appearance of the SMP sheet after the shape-fixing method used in this work. Utilizing the shape fixity of the SMP, various bumpy surfaces were realized. A gear rack was pressed onto the surface of the SMP sheet after making it flexible by placing it inside the drying oven and heating to 80 degrees. And the bumpy surface was then fixed by cooling it to room temperature. Gear racks with modules of 1, 2, 3 mm were used. Hereafter samples 1, 2, and 3. Furthermore, an SMP sheet where the surface shape had not been fixed was used as sample 0. As can be seen in this figure, the spacing between grooves became larger as that modules became larger. This figure shows the shapes of the grooves on the shape-fixed SMP sheet surface. This shows that the groove width becomes larger as the module becomes larger. The experimental device for evaluating the sensor's output is shown in this figure. The gear rack or the jig was placed on the prototype as shown in this figure. The prototype was moved in the horizontal direction by automatic stage, and the output was measured using a multi-input data logger. We conducted two types of experiments. In experiment 1, the gear rack with 2 mm modules were placed on the prototype. The gear rack was affixed to a linear guide that could move linearly in the vertical direction. In the present experiment, the output from element 3 was measured. A frequency component analysis of the output was performed using a fast Fourier transform, FFT, and the frequency that maximized the amplitude was found. Next, in experiment 2, the gear rack in experiment 1 was changed to a jig with a single protrusion as shown in this figure. The protrusion shape was the same as that in the gear rack with 1 mm modules. Using this jig, the same experiment was performed as shown in this photograph. By performing a FFT analysis of the output, the frequency that maximized the amplitude was found. Since an output signal is generated when passing over the bumps, the theoretical value of the frequency that gives the maximum amplitude is taken as the velocity divided by the bump spacing. These figures show the output of the elements for samples 0 to 3 in experiment 1, respectively. It is clear the sensor output values depend on the bump shape on the sensor surface. The spacing between the peaks in the sensor output increases. As the spacing between the bumps increases and the movement speed decreases, like this. The peak amplitude in this figure is larger than that in the other figures. This is thought to be because the bumpy shape of the SMP sheet and the bumps in the gear rack matched. The entire gear rack fit into the bumps on the SMP surface. The output in this figure is smaller than that in the other figures. Likely because the group depth for a module width of 3 mm was smaller than that for the other samples, as shown in these figures. A frequency component analysis of the output was performed using FFT, and the frequency that maximized the amplitude was found. This is an example. This figure shows the frequency at which the amplitude became a maximum between about 1 and 10 Hz, as determined by an FFT. For samples 1, 2, and 3, the frequency increased with increasing velocity. This figure shows the output of the element for samples 0 to 3 in experiment 2. Similarly to experiment 1, the sensor output also depends on the bump shape on the sensor surface. This figure shows the mean and standard deviation of the frequency at which the amplitude became a maximum near the theoretical values, as determined by the FFT, together with the theoretical values. It can be seen that there is good agreement between the measured and theoretical values. Similarly to experiment 1, for samples 1, 2, and 3, the frequency also increased with increased velocity. For samples 0, the frequency did not change, like this. Similarly, the surface shape of target object affects the frequency that maximizes amplitude. Therefore, this frequency can be used to determine the surface shape of a target object. In conclusion, this research evaluated the output from a tactile sensor when it was traced across a bumpy surface using a SMP sheet. Utilizing the shape fixity of the SMP, various bumpy surfaces were realized. The sensor was found to be effective for measuring the surface profile. That's all. Thank you very much.